here see my screen?
Okay, can see.
Okay, thank you. I have not yet see the. Oh, okay, not yet see the Mr. Yusuf. Okay, we wait a few minutes for the first presenter, Mr. Yusuf Sakin. He not yet come the webinar. So maybe we have some minutes for self introduction from the chair and from the audience. Okay, first of all, I would like just briefly introduce me. I'm Thảo, Nguyễn Thảo from Simone University, and I serve the chair for this webinar of the VBEST. And the second is the co-chair, Dr. Đại Văn Võ from the Chongno National University, South Korea. Mr. Văn, can you hear me? Please introduce by yourself. Oh, Văn, he cannot speak.
Yes.
Yeah, okay, thank
I
you.
see.
Yeah, okay, so please the next person who would like to send to you. Okay, very welcome. The audience from the audience, anybody you can share your name and your university or your company. Okay, please. Miss Kulas, can
Hello,
you
yes.
Hello.
okay, hello? Okay, please.
Hello, Professor Tao.
See you. So okay. Okay, Mr. Jacob, welcome.
Yeah, sorry, there was technical problem. So, should I start?
Yeah, okay, not yes. Okay, I will briefly introduce you for 2 minutes. Okay, please. Why? Now, everybody, thank you very much for your attending the 62nd Vietnam Power Electronic Community webinar. And the topic for this webinar is Advanced Control Technique for Electric Vehicle Application. And this in this webinar, we have two presenter. The first one is the Mr. King, and the second one is Mrs. Kulastalibidan. Uh, all the two presenter from the Nazarbayev University, Kazakhstan. Okay, first of all, I the main chair of this webinar, so I will introduce the first presenter, Mr. Joseph Sakin. And after the webinar, the first speaker finished his talk, we will have some discussion regarding his talk, some question or comment for his talk, please talk by yourself or you write the question on the chat box. After that, we move to the second presenter, Mr. Missy Kulas, and Dr. Wang will serve the chair for the talk for the Missy Kulas. Okay, first of all, I would like to introduce the first presenter, Mr. Jacob Sakin, the received the bachelor degree in electronic and nanoelectronic engineering from uh, Alto International University, Kazakhstan. After that, he obtained the master degree in robotics from Nazarbayev University, Kazakhstan. Currently, he pursuing a doctor degree in the Department of Robotics and Mechatronics at the same university. Since 2021, he has been with the power conversion and motion control, laboratory for motion control system. Additionally, from 2022 to 2023, he was research assistant in the Smart Energy Lab for Wireless Power Transfer System at the School of Engineering and Digital Science, the same university. His current research focused on the advanced traction control of electric machine drive, employee electric car and mobile robots, and the present title of the Mr. Yasub today is robust with speed control of electric vehicle with respect to blast and dash time in powertrain. Okay, Mr. Yasub, now I will turn off my screen and you can share your presentation and you can start the presentation. Okay, thank you.
Thank you a lot for the introduction, Professor Tao.
Okay, please share your screen. Okay, I see your screen and your presentation. Now you can start your talk from now.
Okay, sorry, let me arrange. So, good afternoon, everyone. I think it's afternoon in Vietnam. My name is Yusuf Shahin from Nazarbayev University. I will be presenting our recent latest research on robust wheel control for onboard motor electric vehicles. The work's initial results were recently accepted in ICON 2024 and VPPC 2024 conferences. I will be speaking on the behalf of my professor supervisors, Professor Tonduk Do and Professor Bin Min Gwin. Uh, uh, Professor Bin Min Gwin from University of Tokyo and Professor Tonduk Do is from Nazarbayev University. So here is the presentation outline. First, I will motivate what is traction control and its challenges, unique challenges for electrical vehicles. Next, I will show the mathematical model for onboard motor type, drivetrain, identify the obstacles and survey two inertia strategies. Then I will unpack some of the multi-layer disturbance observer system that we propose for this control of electrical vehicle and their stability and robustness analysis and some simulation results. So, and then the last thing is the conclusion. So first of all, I want to start with the traction control and try to explain what is it. So traction control systems are the digital controllers to control the tire-rod interaction in electrical vehicles. Electric powertrains deliver torque almost instantly. Therefore, without an advanced control systems, active regulations on the motor torque, external disturbances and slip can happen. So we need advanced control methods for good efficiency and stability and all above safety for electrical vehicle applications. In general, now we see that advanced technologies like electrical vehicles advanced a lot, like faster than other big industrial technologies. And these traction control technologies are the pivotal and most important recent research active areas currently. So building on that foundation, I can say that electrical vehicles have a lot of types of drivetrain topologies. You can see in the right side, I am showing you two types of topologies. First one is the in-wheel motor configuration, where the motor is directly connected to the wheel. Or sometimes we have hub motors, which also puts the motor inside the wheel. So wheel and motor is directly connected to each other. However, if you check the figure B, you will see onboard motor type configuration. And here we can see that there is gears, differential or other elements that transfers the torque generated by motor to the wheel. So there is not direct connection, but there is some extra arrangements, configurations to deliver the torque. And if we check the previous studies, speed control is simplified, where the dynamics neatly used as a first order plant, 1 over JS. And this assumption is not valid for onboard motors. They are mainly valid for only in-wheel type motors because motor is directly connected to the wheel. But on board, we have a different type of mathematical model. So our research targets this tougher newly topology and control for it. So to explain it, to clarify it more, I want to explain the mathematical model. Here you can see that figure 5 shows the two inertia block diagram, which how we explain the onboard motor EV configuration. So we are linking the motor shaft using a differential and then differential to the wheel. Here are the governing dynamic equations. So we have two inertias, and these two inertias connected through a torsional stiffness and damping. And then if you check the upper part of figure 5, we see the tire rod dynamics, which we have the slip ratio and the magic formula. I want to specifically talk about the figure 4, the friction to slip ratio curve. Here we can see that maximum friction coefficient means the maximum traction is achievable in around 0.1 to 0.2 region. So our control approach is to get the maximum traction as possible to avoid the slip. Therefore, our control should keep the slip ratio between this range to able to get the maximum traction. And if we come to the design challenges for onboard motor EV, we can see these four big topics. First one, because of two inertia system, we have a higher order plant dynamics. So if we derive the transfer function, we see that we have a third order plant. Then we have couple nonlinearities like backlash, saturation, and tire rod interaction. These are some of the nonlinearities that we see in the model. Third one is the communication latency. The CAN bus communication brings 5 to 20 millisecond varying delay to the system. So we have two types of delay here. First one is the torque command, and the second one is the feedback, sensor feedback. So both of them affects to our control system. And fourth one is the wheel speed feedback. So some of the low cost OBM electrical vehicles omit the encoder for wheel to reduce the cost. And this creates a problem because we are trying to control the wheel speed rather than the motor speed only. That's why we need an wheel speed feedback. Here I want to show you some little literature, how recently in last 5 years, how people dealt with two inertia systems, especially for the backlash nonlinearity. From the literature, we see that it offers different type of methods. First one is classical, PID. Second one, they use backlash inverse model to compensate the backlash effect. Third one is the observer or estimator's design that estimates and gives this estimation as a feedback to handle the nonlinearities or disturbances. The fourth one is the sliding mode control, which allows us to design and higher order controllers and higher order observers. And fifth one, last one is the neural network based methods. So all these control approaches have their advantage and disadvantage based on application. And for our application electrical vehicle, we wanted to focus on designing advanced disturbance observer system. So here is our proposed method. In figure 6, you can see our contribution. It's a cascaded disturbance observer based control loop. So we have a first observer to estimate and compensate the disturbances acting on the motor in the drivetrain. And second observer estimates the wheel speed and gives it as a speed feedback for the speed control loop. So implementation is very straightforward and very powerful because the observer designs can estimate all type of disturbances on the system, including the nonlinear disturbances. Here you can see the equation 6 and 7 shows the disturbance observer equations. Qt and Q omega are the low pass filters that we need to tune according to our system. And we use the PI controller for the speed control loop. So I mentioned 4 types of problem: backlash, time delay, nonlinearities, backlash nonlinearities, time delay, and speed feedback. So first I want to talk about the time delay part. Here is some analysis that we provided for the delay. When we derive the transfer function, assuming the omega L and omega M are same for simplicity, we can see that we have an stability or robustness until 12 milliseconds of time delay. So we can model the time delay from torque command to the electrical vehicle, and we can model another one for the feedback. And when we check using stability analysis, we see that the system poles are stable until 12 milliseconds. And later I will show the simulation results with such high delay. So second one for the nonlinearities. For nonlinear system analysis, we can use one of the popular methods called the circle criterion, which checks the system stability and robustness based on the bounded nonlinearity. Here we bound the nonlinearity based on the saturation limits. So we know the upper limit and lower limit of the saturation nonlinearity, and we insert these limits to the circle criterion method to get the stability. So I can just easily explain that circle criterion method says that a system is stable when the open loop Nyquist curve avoids the circle determined by these sector bound, these upper and lower bounds of the nonlinearity, with all the poles already in the left half plane. Here I have some Nyquist plots to show you. Figure 9 shows that the Nyquist plot of the transfer function respect to the bounded nonlinearity. So we have the upper and lower bound for our nonlinearity, and we draw the circle for the circle criterion method. And here we see that our parameter variations, our system's robustness to the parameter variations are very high. So we can see that omega and omega L has very good robustness to parameter variations. And we have another parameter called the torsial stiffness. And we can see that also it has very good level of robustness to the parameter variation. And I want to talk about the simulation results. We have conducted two types of simulation. First one is using a worldwide harmonized light vehicle speed test, VLTP. This is one of the standards for testing the wheel speed tracking performance, management performance. So we have simulated using the, so our simulation results that I will show you is consist the first 100 seconds of full speed pattern. And figure 11 shows the estimation performances respect to different time delays in our system. So we can see that even if you have high delay, our system still able to follows the speed pattern very effectively. And our estimation performance is also very effective. Here is the speed tracking performance, figure 12. We also conducted parameter variation for the mass because in real electrical vehicle applications, the mass can vary a lot. So for even mass, 50% of mass change, it is very robust. And we added slope condition to check some different type of electrical vehicle condition, driving condition. So when the vehicle drives on a slope, drives up on a slope, still we can see that even when the disturbance is very high, because of this slope, the vehicle can, the control system can adapt to it and fastly, like the performance of this inclined road scenario is also very good. And before I said that we have to keep the slip ratio between 0.1 to 0.2 to get the maximum traction. And we can see from the simulation result that we are getting a very good slip response. Even for the worst scenario that we were trying to show when the time delay is high and we have a high slope scenario. Second simulation that we conducted is using the new European driving cycle. So this is another standard driving pattern for the testing electrical vehicles. So here are the estimation results for our disturbance observer designs. We can see that the estimation performance is good. And here we check the parameter variations. So here you can see that even when it is very high parameter variations like 2 times, the system introduces just small oscillations. Same goes for the vehicle mass variation. So to conclude, we modeled an OBF drivetrain as a two inertia system with a delay and uncertainties and non-linearities. We embedded a cascaded layer, multi-layer disturbance observer inside our control system. We provide a stability and robustness analysis using circle criterion method to check to validate the robustness against nonlinearities. We have simulated, we have shown some simulation results using the popular VLTP and NetC speed pattern scenarios, these payload, vehicle mass, inclined road scenarios. The good part of our approach is that this control approach is very straightforward and can be implemented with real hardware. Therefore, our next step, future work, will focus on integrating this system to a real scale EV hardware setup to test the effectiveness in real experiments. Below, here you can see the 2 published conferences papers. For more details, you can check it. And here are the references. So thank you a lot. for your time
Okay, thank you very much,
listening.
Mr. Yusuf Sakins, for very interesting presentation and informative. So, any question or comment from the audience for the presenter? Please raise your hand and directly ask the presenter. Okay, if you also would like to uh, follow the, you can talk, you can take your question also in the chat box, and I will transfer to the presenter. Okay, please. Any question or comment, please?
Yeah, not just questions, maybe discussions also possible.
Mm,
Yes, if anyone has ideas.
yeah. Only comment also okay. Okay, so please, Mr. Khan MD Jacob Ali. So please, uh, directly ask the question, please. Mr. Jacob, please ask the question. Yeah, please.
Thank you, Sensei. Firstly, I just introduce myself. I am Khan MD Yakub Ali Khan, and my supervisor is Nangya Mintham, is our respective chairperson. And my main title or main research proposal is motor drive systems, cars, and EVs. So recently, I just some researches recently, new researches to be ongoing is that disturbance observer. So my first question is, what is the purpose of using cascaded in the disturbance observer in wheel speed control?
Okay. Do you have any questions?
I have an one question is that who is the purpose the using cascaded disturbance observer in wheel speed control?
Okay.
Maybe
So
this page number is 5. Yeah.
so here you can see that in onboard vehicle types, we have a two inertia
Yes.
system.
Oh, that's great.
Okay. So you can see
Yes.
that motor inertia is 1 over Jm S plus Vm. So here the below one is the motor plant and up inertia is the wheel plant. So here actually if you check the figure 3 you will understand it more. Motor is
Yes.
connected to a differential and
Oh.
differential is connected to the wheel. So what I said here in design challenges, some cheap low-cost OBM motor platforms, EV platforms, omit the using the sensor for omega L, so wheel speed. So they just use encoder the feedback for motor, but they don't have it for the wheel to reduce the cost of electrical vehicle. Then we have the problem. Now we are trying to control the wheel speed omega L, but we have only information of omega M. Therefore, we use the cascaded approach to able to estimate the wheel speed.
Okay.
First, so if I explain from the figure 5, first our
Yes.
first DOB is estimating or observing the TL from motor plant characteristics and TM. After we are estimating the TL, we can use TL information and omega information to get the omega L estimation. So this is our approach to estimate omega L.
Okay. Thank you so much.
So our inner loop, the first estimation works for motor disturbance compensation. It estimates the external disturbances acting on the motor and compensates for as a feedback. And later using that feedback also for second observer to able to estimate the wheel speed to have the wheel speed control loop. This is our propose.
Oh,
in
okay.
this research.
Oh, thank you. Thank you so much.
Thank you.
Okay, thank you so much, Mr. Jacob, and also the presenter for the very nice question and answer. Okay, we have any more comment or question for the presenter, please? Okay, inviting for the author audience question. So, Mr. Joseph, I have a question regarding the friction efficient. So, please move to the slide with the friction. No, no, no,
This
no,
one,
friction efficient. Okay, here, figure 4. So, uh, I remember 5 and 4 years ago, I also have the research regarding the power assist electric vehicle mobile robot with the friction coefficient. So how can you determine the friction coefficient exactly? According to this figure, how can
okay.
you determine the friction coefficient? You divide the four environment: dry, wet, snow, and ice. Okay, it means environment on the surface, road surface between the surface and your wheel. I understand, but how can you determine the uh, the light, the blue light, the red light, the black light, and green light? You use the from the auto work, or you determine by yourself?
Uh,
Okay.
okay. These four different type of asphalt
Mm,
conditions, dry, wet, ice, snow,
mm,
uh, are well known from the Pajeshka magic formula.
mm.
So if you check
Magic
the
formula. You use the
literature,
magic formula. I understand. Okay.
yes, so each of them has different values in magic formula, and
Mm.
after we insert these values, we get this plot.
Mm, okay. Okay, you use the
So
magic formula and you just inject the strip ratio value and you receive the friction coefficient, right?
uh,
Mm,
yes, but this is friction coefficient to slip ratio curve. So it is
mm,
not just the friction coefficient of the dry asphalt. So it is the relation between the slip ratio to friction coefficient.
mm.
Yes.
Okay. So in your study now, you only focus on the dry tamas, yeah, dry it in the black light, only the dry environment.
For now, until now, we have only conducted simulations.
Yeah.
However, uh, uh,
Mm,
hopefully, when we start experimenting, we will probably conduct dry and wet tarmac. But in
mm,
general, for safety reasons,
mm,
we have the control loop always should keep the slip ratio less than 0.3 for the safety purposes. Otherwise, it means that it is slipping. So it can be dangerous for driving or other purposes.
mm. Yeah, understand. So okay, the
So
last small question is you know do simulation. I understood that. But simulation in that simulation you use only consider the fresh surface, or you can consider the slope. Your vehicle can move to on slope or only flat surface.
we conducted two types of
Oh
simulation.
yeah.
When we used the new European driving cycle, it was flat, so there was no slope. So
Only
in
flat. Yeah.
yeah,
Mm,
flat surface, different type of speed reference. But
understand.
when we used worldwide harmonized lightweight
Mm,
vehicle test procedure, here you can see that we added some slope.
yeah. Okay. It's good. Okay. Thank you very much. I understood clearly. Okay, so any more question or comment for the first presenter, please? Sorry. Okay, Mr. Yusuf, I have another question from the audience from the internet. He is transfer to me. Okay, I now transfer to you.
Yes.
He see that your research focus on the using of the DOB, disturbance of observer. Okay,
Yes.
and the audience he used the high order sliding mode observer for the same control objective, same the control objective with you. So,
Yes.
but he used the high order sliding mode observer. You use the cascade DOB. Okay, can you have any give any opinion or experience comparison between the cascade DOB, your method and his method high order sliding mode observer? Can you have a experience for comparison or opinion regarding the two methods? Okay, please.
So here, when we check the recent studies, we see that both methods actually very popular.
Yeah, right, right,
Disturbance observer and the sliding mode also. However,
right.
we didn't conduct experiments yet. That's why I cannot comment from experimenting
Yeah.
part. But from the literature, I can say that sliding mode control allows us to design a better higher order observers or control systems. However, implementation becomes more difficult.
Mm. Implementation is
Disturbance,
more difficult.
yes, disturbance observer with PI is a more simple or straightforward method. If they give similar results, probably disturbance observer based method will be easier to implement in experiments. Because we are talking about very complex dynamic system. Therefore, that's what I think. Like probably sliding mode control might be very hard to implement initially.
Okay.
However,
Okay, I understand.
they can check Professor Min's recent papers. They have also some papers with sliding mode, comparison with
Oh,
sliding mode. So they can check those papers actually.
okay.
But there they don't focus on two inertia, the OBM EV. They focus on in-wheel EV
Oh,
structure.
um, okay, I understand your comment and your opinion regarding the two methods. So, okay, maybe we have some different regarding the objective. Yeah, okay, the objective or and uh, your consideration. Okay, you choose disturbance observer. No problem. It's a very good explanation. So, okay, any more question or comment for the first presenter? Okay, maybe no. Okay, thank you very much, Mr. Joseph. So it's a very good presentation and nice information. Okay, thank you
Uh,
very much. So, okay,
Thank you. If you have more questions, you can actually contact
yeah,
us
okay,
using my email, or this is our
yeah,
website
mm,
to connect with our professor.
okay, thank
Thank you
you.
a lot.
Okay, so now we move